Data center cooling isn't just about keeping servers comfortable. It's about maintaining operational efficiency, preventing hardware failures, and managing one of the largest operational expenses in modern computing infrastructure. In this video, I'm going to walk you through the critical cooling technologies that keep the digital world running. Every server, switch, and storage device in a data center generates heat. A single rack can produce anywhere from 50 to 30 kilowatts of thermal energy. Multiply that across thousands of racks, and you're looking at megawatts of heat that must be continuously removed. If we don't manage this effectively, equipment fails, performance degrades, and operational costs skyrocket. The physics here are straightforward but unforgiving. Modern processors can reach junction temperatures of 90 to 100 degrees Celsius under load. At these temperatures, silicon degrades faster, solder joints weaken, and the risk of thermal runaway increases exponentially. We're not just cooling for comfort, we're cooling to maintain the fundamental integrity of the hardware. And with server densities increasing year over year, the challenge only intensifies. What worked 5 years ago is inadequate today. Let's start with the foundation, air cooling. The most common approach is the hot aisle, cold aisle configuration. Server racks are arranged in alternating rows. Cold air is supplied through perforated floor tiles in cold aisles, where server fronts face each other. Servers pull in this cool air and exhaust hot air into the hot aisles behind them, where it's returned to the cooling units. This simple arrangement prevents hot and cold air from mixing, which dramatically improves cooling efficiency. When hot and cooled air mix, you create thermal gradients that waste energy and create hotspots. Hotspots are the enemy of reliability. A single poorly cooled server can throttle performance, creating cascading problems across your infrastructure. Many facilities take this further with containment systems, physical barriers that completely separate hot and cold air streams. Cold aisle containment closes the cold aisles with doors and ceiling panels, creating a pressurized environment. Hot aisle containment captures the hot exhaust before it can mix with room air, directing it straight back to the cooling units. The choice between cold and hot aisle containment depends on your facility design, but both approaches can reduce cooling energy consumption by 20 to 40% compared to open configurations. Airflow management is equally critical. Blanking panels fill unused rack spaces to prevent air recirculation. Cable management ensures cables don't block airflow paths. Even the placement of perforated tiles matter. You want cold air delivered precisely where servers intake it, not wasted in aisles or under empty racks. CRAC and CRAH units are the workhorses of data center cooling. CRAC units, computer room air conditioning, use mechanical refrigeration, similar to your home air conditioner, but on a much larger scale. They're precise, reliable, and can handle high heat loads. A typical CRAC unit can remove 10 to 30 tons of cooling, which translates to 120,000 to 360,000 BTUs per hour. These units use direct expansion refrigeration cycles. Refrigerant evaporates in the cooling coils, absorbing heat from the air, then gets compressed and condensed outside the data center, releasing that heat. The advantage is precision. CRAC units can maintain tight temperature and humidity tolerances, which is critical for sensitive equipment. The disadvantage is energy intensity. Compressors consume significant power, and efficiency drops as ambient temperatures rise. CRAH units, computer room air handlers, use chilled water instead of refrigerant. They're more energy efficient and better suited for large-scale operations. The chilled water comes from a central plant, which can use cooling towers, chillers, or even free cooling from outside when temperature permits. CRAH units are essentially large fans and heat exchangers. Chilled water flows through coils, air passes over those coils, and heat transfers from the air to the water. The warmed water returns to the central plant to be cooled again. The efficiency advantage comes from separating heat rejection from air handling. Cooling towers can reject heat using evaporative cooling, which is far more efficient than mechanical refrigeration. And when outside temperatures are low enough, you can bypass chillers entirely and use the cooling tower alone. This is called waterside economization, and we'll talk more about that shortly. As server densities increase, air cooling reaches its limits. Air has low thermal conductivity and low heat capacity, Moving enough air to cool a 50 kilowatt rack requires massive airflow and creates acoustic problems. That's where liquid cooling comes in. Water has roughly 35 times the heat capacity of air, making it far more efficient for high-density applications. Direct-to-chip liquid cooling uses cold plates mounted directly on processors and other high-heat components. These are precisioned machined metal plates with internal channels. Coolant, typically water with additives, flows through these channels, absorbing heat at the source. This approach can handle heat loads exceeding 100 kilowatts per rack, impossible with air cooling alone. The advantage is thermal efficiency. You're removing heat right where it's generated, before it can spread to surrounding components. This allows higher processor frequencies, denser rack configurations, and quieter operations since you're not relying on high-velocity air. The challenge is complexity. You need leak detection, redundant pumping systems, and careful maintenance. A coolant leak in a data center is a serious incident. So when do you actually need liquid cooling versus air cooling? It comes down to power density and total cost of ownership. For traditional enterprise workloads, web servers, databases, general compute, air cooling is still the most practical choice. If your racks are consuming 5 to 15 kilowatts, air cooling is a proven, reliable, and cost-effective solution. The infrastructure is simpler, the maintenance is straightforward, and the risk profile is well understood. But when you cross into high-density territory, 20 kilowatts per rack and above, air cooling becomes problematic. You need massive airflow, which means more CRAC units, higher fan speeds, and acoustic issues. At 30 to 40 kilowatts per rack, you're pushing the practical limits of air cooling. This is where we see liquid cooling becoming necessary, not just beneficial. High-performance computing is the obvious use case. Supercomputers, AI training clusters, and machine learning infrastructure routinely exceeds 50 kilowatts per rack. NVIDIA's DGX systems, for example, can consume 10 kilowatts per GPU server. When you're packing 8 of those into a rack, you're looking at 80 kilowatts or more. Air cooling simply cannot handle this effectively. Cryptocurrency mining is another area where liquid cooling has started to become the gold standard for large operations. Mining rigs run at maximum load 24/7, generating consistent high heat output. The economics favor liquid cooling because the energy savings offset the higher capital cost over the equipment lifetime. The decision also depends on your facility constraints. If you have limited space and need maximum compute density, liquid cooling lets you pack more servers into the same footprint. If you're in a region with high electrical costs, the operational savings from liquid cooling's efficiency can justify the investment. But if you have abundant space, cheap power, and moderate workloads, air cooling remains the rational choice. The industry is moving towards hybrid approaches. You might have air-cooled racks for general-purpose workloads and liquid-cooled for high-density compute, all in the same data center. This gives you the flexibility to match cooling technology to workload requirements without over-engineering your entire facility. Rear door heat exchangers offer a middle ground. These mount on the backs of server racks and cool exhaust air before it enters the room. They use chilled air but don't require modifications to the servers themselves. You get some of the benefits of liquid cooling without the complexity of cold plates. Immersion cooling takes this even further. Servers are submerged in dielectric fluid, a non-conductive liquid that won't damage electronics. The fluid absorbs heat directly from all components, eliminating the need for fans and dramatically reducing energy consumption. Single-phase immersion keeps the fluid liquid. Two-phase immersion allows the fluid to boil, which provides an even better heat transfer through phase change. It's still emerging, but it's becoming viable for high-performance computing and AI workloads where power densities exceed 200 kilowatts per rack. Microsoft's Project NATEC demonstrated two-phase immersion cooling in an underwater data center off the coast of Scotland. The operational benefits are significant. No fans means lower maintenance, better reliability, and near silent operation. But it requires purpose-built infrastructure and careful fluid management. Why use energy to cool air when nature can do it for you? Free cooling leverages outside air when temperatures are low enough. This is one of the most effective ways to reduce data center energy consumption, and it's why you see major facilities being built in cooler environments. Airside economizers bring in filtered outside air directly when outdoor temperatures are below your set point. Instead of running chillers or CRAC units, you're just using fans to move air. The challenge is filtration and humidity control. Outside air carries particulates, pollutants, and moisture that can damage equipment. You need robust filtration systems and sometimes supplemental dehumidification. Waterside economizers use cooling towers to chill water without running mechanical chillers. Cooling towers work through evaporative cooling. Water evaporates, absorbing heat and cooling the remaining water. When outdoor wet bulb temperatures are low enough, cooling towers alone can provide all the cooling you need. This is incredibly efficient because you're only running pumps and fans, not energy-intensive compressors. Facilities in cooler climates can achieve significant energy savings, sometimes running entirely on free cooling for months at a time. Facebook's data center in Prineville, Oregon, was one of the first hyperscale facilities designed for 100% outside air cooling. It achieves a PUE of 1.08. Google's facility in Hamina, Finland uses seawater from the Bay of Finland for cooling, achieving similar efficiency. Even in warmer regions, partial free cooling during nights and cooler seasons reduces operational costs. The key metric is the number of free cooling hours per year. A facility in Iceland might get 8,000 hours, a facility in Phoenix might get 2,000. That difference directly impacts operational expenses and PUE. Power usage effectiveness, or PUE, is the industry standard metric for data center efficiency. It's calculated by dividing total facility power by IT equipment power. A PUE of 2.0 means that for every watt powering IT equipment, another watt is used for cooling, lighting, power distribution, and other infrastructure. A PUE of 1.5 is good. Modern, efficient facilities achieve 1.2 or lower. The theoretical minimum is 1.0, which would mean zero overhead. Impossible in practice, but it's the target we're working towards. PUE has limitations. It doesn't account for water usage, which matters in water-scarce regions. Google introduced water usage effectiveness, or WUE, to address this. It doesn't directly reflect IT efficiency. You can have a low WUE running inefficient workloads, and it can be gamed by measuring at favorable times or excluding certain systems. The Green Grid, which developed the PUE metric, has published detailed measurement protocols to standardize reporting. But despite these limitations, it's a useful benchmark for comparing facilities and tracking improvements over time. Improving isn't just about better cooling technology. It's about optimizing airflow, eliminating hot spots, raising temperature set points safely, and matching cooling capacity to actual heat loads rather than over-provisioning. Many older facilities were designed with excessive cooling capacity because of conservative assumptions. Modern approaches use computational fluid dynamics modeling to optimize airflow and right-sized cooling infrastructure. Temperature set points matter significantly. ASHRAE Technical Committee 9.9 has progressively raised the recommended temperature range over the years. Their 2021 guidelines now allow inlet temperatures up to 27 degrees Celsius for most equipment, with some classes tolerating up to 35 degrees. Every degree you raise the set point reduces cooling energy by approximately 2 to 5%. But you need monitoring and controls to ensure that you're not creating hotspots or risking equipment reliability. It's a balance between efficiency and risk management. The future of data center cooling is being shaped by several trends. First, modular and distributed cooling. Instead of centralized CRAC units, we're seeing in-row cooling units placed directly between server racks. This shortens the path between heat generation and heat removal, improving efficiency and reducing the need for raised floors. AI and machine learning are optimizing cooling in real time. These systems predict heat loads based on workload patterns, weather forecast, and historical data. They adjust cooling set points, fan speeds, and airflow distribution dynamically to minimize energy while maintaining reliability. Google's DeepMind AI reduced cooling energy consumption by 40% in their data centers back in 2016, and they've continued to refine this approach. Their system uses neural networks trained on historical sensor data to predict future temperature and pressure conditions, then recommends optimal actions. Microsoft has implemented similar AI-driven systems across their Azure data centers. These approaches are now becoming more accessible to smaller operators through commercial building management systems. And as sustainability becomes critical, we're seeing waste heat recovery. Using data center heat for district heating, industrial processes, or even greenhouse agriculture. Stockholm Data Parks in Sweden has become a pioneer here, supplying waste heat to the city's district heating network since 2018. Meta's data center in Odense, Denmark, provides heat to 100,000 residents. In colder climates, waste heat warms greenhouses. There's a facility in the Netherlands using data center heat to grow tomatoes year-round. This doesn't improve PUE directly, but improves overall efficiency by making use of heat that would otherwise be wasted. We're also seeing regulatory pressure. Denmark now requires new data centers to connect to district heating networks where feasible. The European Union's Energy Efficiency Directive mandates that large data centers report their PUE and implement energy management systems. Singapore now requires data centers to achieve a PUE of 1.3 or better and use best-in-class cooling technologies. This regulatory pressure is driving innovation and forcing the industry to take efficiency seriously. Data center cooling is a complex, evolving field that balances performance, efficiency, and cost. Whether you're using traditional air cooling, advanced liquid systems, or hybrid approaches, the goal remains the same: remove heat efficiency, maintain reliability, and minimize environmental impact. As computing demand grows and sustainability pressures increase, cooling innovation will remain at the heart of data center design.